I hope it wakes you up. It makes me feel less awkward just waiting till exactly 15:15. Very good. That's a group called Go-Go Penguin. Go look them up. Just before we start, I just thought a couple of meta comments. I'm just picking up a vibe from students from questions they've asked and also reflecting on my experience 2 years ago. I know I'm overwhelming you with material. Try to get used to it. The point is, it's the norm outside of school, right? Most of your education to date, you've been given it in bite-sized chunks. I'm giving you the banquet, and you have to pick and choose. It's deliberate. And learning to deal with that is one of the learning outcomes of the course, and I'm happy to help you with it. There's other reasons for doing so. The topic we're studying, it's not a single thing. It's not just learning linear algebra and eigenvectors, right? It's a complicated thing, so we're looking at it from many, many different directions. That means a lot of material. As computer scientists, or whatever you think of yourselves as, we can't solve the ethical problems of machine learning just using our home disciplines, so we have to look afar, and that's challenging because different disciplines write completely differently. I'm looking for controversy. Right? I'm deliberately looking for controversy because a lot of the questions that we're asking don't have a single simple answer. And I repeat again, just because I give you a big stack of stuff to read, I'm expecting you to pick and choose, not to try and read all of it. The first several lectures, today included, does have a lot of maths, and as I'm just reminding you, my logic is that's the way we connect to machine learning, which is intrinsically mathematical. One of the hardest things of presenting any large thing, when you get to write your thesis or give a long series of lectures, is putting it into a linear order. The world's not linearly ordered, right? I have to choose an order because time's one-dimensional, but there's many ways we could have done it. So if it seems a little confusing, that's part of the reason for it. And all I'm asking you to do is to attend the lectures, engage in the tutorial, but then spend quite some hours per week doing the reading, thinking about it, discussing it amongst yourselves, right? Preparing for the essays that you will have to write. Okay, into today's lecture. Perhaps a little surprisingly, apropos of looking a little sideways, we're going to look at a thing called the 4 elementary forms of sociality, what it means to be social, and an interesting connection between that and the way you do numerical measurements. And then those two things together actually give us some insight into how we aggregate, right? And I've already introduced this idea of looking at different ways of aggregating as an approach to fairness. So we'll look at that, we'll look at it axiomatically, we'll look at the question, suppose you've got 2 ways of aggregating, you want to combine them together. We'll look at the ethical principle behind many of the approaches to fairness, which essentially is throttling information. And we'll meet this famous thing called the veil of ignorance. I'll show you an impossibility result and a technical mathematical representation of these risk measures that we met last week, which allows us to, I think it gives us very nice insight into how we tune our ethical principles. All right, I've said already many times that there's no one way to solve these problems, and so we come up with some nice knobs. So, the first topic is quite a mouthful, the 4 elementary forms of sociality, measurement scales, and utility aggregation. So, whatever this thing that we've been thinking about, fairness, it seems to have something to do with society, with groups of people, or with sociality. Now, this is not a course on sociology, but it is interesting from our perspective and insightful, I think you'll find, to think about what is the basis of the social. Like, what does that even mean? And there's a gargantuan literature on that. You might know some people here studying sociology. They'll spend their whole degree on it. I'm going to lean on this intriguing book that came out, I guess, 10 years or so ago called Structures of Social Life, which, you know, for a mathematician is appealing because he breaks it down into quite mathematical concepts. So he distinguishes what he calls the 4 types of sociality. Imagine different kinds of societies and what makes them social. There's communal sharing, right? You live in a share house, you know what this means, right? There's authority ranking. I'm the boss, you're not, right? There's equality matching. We have a cake, we divide it up into equal sized pieces, right? There's for any good. And market pricing. Everything's got a price, you buy and sell, right? So Fisk argued, using extensive field work across many societies, not just Western societies, all around the world, how these 4 types of sociality essentially capture pretty well most of human experience. So my view on this is it's an interesting lens to look at our problem through, right? And the intriguing thing is a connection made to something quite mathematical. Now, I know you can't read this and absorb it just sitting in the class. There's 3 slides like this, which I've taken from one of his papers, where he elaborates this, right? So if you don't want to go and read the paper that I point you to, you can just look at this and you'll see he's fleshing this out. This is not just some abstract idea. He's looked at it in fine-grained detail. I really can't go through this, but you can look at the slides. There's three pages of slides with all of this material, where each column here is, the 4 columns on the right are the 4 types: communal, sharing, authority ranking, equality matching, and market pricing. And he looks at the different aspects of society, right? So it's this big matrix, so big it doesn't fit on one slide. I think that's worth looking at. It's intriguing. Is it true? I don't know. Does every sociologist agree with it? Certainly not. Is it helpful for our purposes? Yes. To get to the point that I want to make, I now have to introduce another notion, which is fundamental in most of the stuff engineers and technologists and scientists do, and that is measurement, right? So we're doing machine learning. Machine learning is viewing the world through numbers. And where do those numbers come from? So, sad to say, in many cases, you just download them from a website, right? But if you're doing it seriously, what you would be doing is you'd go out and measure stuff. Measurement is turning something in the world into numbers, right? You're reducing the rich complexity of the world into some numbers. Now, some people don't even like that idea. This is William Blake's painting of Newton, right? I don't think Newton was that buff, and he didn't walk around naked either. But the usual interpretation of this painting is that look at this, glorious complexity of the world, right, all around him. And what's Newton doing? He's on his computer, right? If he had an iPad, he'd be on his iPad. He's drawing with his compass. He's mathematizing the world. He's throwing away all of that complexity, just reducing it to numbers. That's what we all do. We're all buff, naked Newton sitting on a rock. Keep that image in your head. Anyway, if you're interested, like if you're doing art history as well as computer science, I gave you some pointers where people write great long essays about this painting. It's kind of interesting. But there's also a very interesting story in the reference in pink about this very notion, right, which is at the heart of what we're doing in the first half of this course, of turning something as nebulous as ethics into mathematical calculation, right? That's what we have to do to bridge into the world of machine learning. And that's the point that many people get jack of, right? They won't accept that you can even do that. It's interesting to keep that in mind. Now, nevertheless, the scientists and the engineers of the world are preeminent at the moment. This is Lord Kelvin, very famous scientist, and there's this very famous quote that he made, which is worth reading in full. I often say that when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, and when you cannot express it in numbers, your knowledge is of a meagre and unsatisfactory kind. It may be the beginning of knowledge, but you've scarcely in your thoughts advanced to the stage of science, whatever the matter may be. Right? It's kind of fighting words. Remember, what we're doing is we're measuring fairness. If we want to stick it into our objective function, we've got to turn it into numbers. Right? So, there's an authority figure for you. He's got the beard and everything. So this is his claim. If you can't put it into numbers, then, you're just not even trying. A lot of people took this to heart. Chicago economists, right, the intellectual foundation of the modern theory of neoliberalism, they carved it into stone on their building. They thought it was so good, although they didn't have a big enough building to put the whole quote, so of course they had to contract it. And Thomas Kuhn wrote a nice little essay talking about that. But the point I want to make is that it's, often with these things, these famous quotes, they're taken out of context. And it's always good to go and look at the original and see what comes afterwards, because often you get the wrong impression. So here's what come afterwards. He's talking, he goes on to complain about, so he's writing in like 1900 or something, 1889. People are starting to understand things like materials, why some steels are harder than others, why diamonds are really hard and why gypsum is not. So nowadays, if you study material science, you've got a very quantitative way of dealing with that, but back then they didn't. So he says this regarding that. We've got no exact understanding of what this property of hardness is. Like, you can use the word hardness, right? This doesn't have a lot of hardness. This has more hardness. It's a thing, right? Nor of how it is related to moduli of elasticity or to tensile or shearing strength or to the quality of the substance in respect to its bearing stresses exceeding the limit of its elasticity. All of those technical terms he's rattling off, they're things that were understood at the time to do with materials, how materials behaved. And what he's complaining is that we still don't understand how to relate them to hardness. Anyway, the clear analogy that I'm making is hardness, fairness, right? Hard, fair, 2 4-letter words, nice and simple. But what he's essentially demanding is a quantified version of that. So that's what we're trying to figure out. So that's the idea of measurement, but it's all very well to go and say, turn the world into numbers. That doesn't really solve your problem, does it? It just gives you a bigger headache, because you can immediately then say, well, but how? Right? I can just assign the number 7 to this desk. That's pointless. You have to have some kind of rationale or theory for it. And there is a theory called measurement theory, right? There's books written with that title, measurement theory, and they grapple with that very question. How do you go about measurement? And the warm-up is that you make a little bit of a typology on the types of things that you would measure. So as one warm-up, I talk a little bit about this in the Fairness Risk Measures paper that you would have looked at last week, so footnote 4 of that. If you've done any physics, you must have done some dimensional analysis. So the idea is, suppose you had 2 quantities, like, my height in meters and the temperature of the room, right? They're both numbers, right? I'm 182 high in centimeters and the room is 20 degrees. Is it legitimate to go 182 plus 20? No, it's idiotic. It's a type error, right? So dimensional analysis keeps track of the units, right? So that begs the question, what are the units of fairness? We know the units of length or hardness or temperature, but what are the units of fairness? That's too difficult a problem. We can go and ask the question, what are the units of losses? We use loss functions in machine learning. A loss function is just an outcome contingent disutility. Remember, where H is the hypothesis and Y is the outcome. So that gives us a number. All of our machine learning algorithms are optimizing this thing. It's like, that's what we're paying attention to. So what are the units of them? They're normally positive numbers. We can always assume that. They're bounded. They're usually bounded. And in particular, one way of approaching this question, right, we can't go and say, what are the units? There's no predefined unit, but we can go and ask what's legitimate to do with them. The example I gave before of adding height and temperature, that's an illegitimate operation. What are the legitimate things that we can do with these losses? Why do we want to answer that question? Because that sits underneath one of the proposed approaches to fairness that I gave you. Now, economists do have an answer for this. You ask an economist what are the units of utilities, and he'll quickly answer they're utils. But this is just a linguistic trick. right? This is just defining the word utils. We don't really know. So this was a little bit of a dead end, right? It doesn't actually illuminate what is going on. What does help is this notion of scale types. So the way you understand the type of measurement that you're doing is you consider the set of transformations that are considered legitimate. So a nominal, let's call a nominal measurement any one-to-one map, right? So the numbers themselves don't mean anything as long as there's some kind of correspondence. An ordinal transformation is any monotone, increasing and continuous map. So this is one just to think about. We measure certain things, like, maybe I measure the height of you, and I do it in a dodgy kind of way, but in such a manner that I always preserve the ordering. So I don't know that you're 168 centimeters high, but I do know that the fellow next to you is a little higher. I can't actually quantify it, but I've preserved the ordering, right? I've captured something about it. You can see the analog with fairness there. You might not know the actual amount of fairness, 3.7 international units of fairness, but you might be able to say, well, at least this is more fair than that. So that's something. You can have a ratio transformation where any scaling, I can use volts or I can use millivolts, right? I just multiply by 1,000, right? Nothing's really changed. I can translate, right? So I can measure the height of the building relative to the ground or above sea level. And an interval scaling is a combination of these two. So basically any affine transformation. So these are standard names now in the literature. You could interpret, with the benefit of hindsight, Kelvin's complaint about material hardness is by saying that the mere ordinal scales are inadequate, you'd like an interval scale, right? You can go and get a whole bunch of different materials and you can say this one's harder than that. I mean, how do you do that? You just take material 1 and see if you can scratch material 2. Right, if I have a diamond, I can scratch the glass, but the glass can't scratch the diamond, therefore the diamond is harder. If you want to quantify it, you've got to go a little further. So this idea, due to this fellow called Stevens a long time ago, 1955, had the notion that the statistics that you do on your measurements should, what does he state? The statistics applicable to a given scale are those that remain appropriately invariant under the transformation permitted by the scale. He's restricting the calculations that you can do to align with the group of transformations that you allow. Anyway, so this was quite an insight, and it's, as I'm about to show you, it's directly related to our questions about merging functions. So remember last week or the week before, the last lecture I gave you, I showed that if you just take all of the individual loss values, right, you have a predictor, you evaluate it on each data point, you get a loss per data point, and normally you just take an average, and that's the thing you try and optimize. And I showed you that you could use some other sort of thing. What we're doing is we're aggregating a bunch of numbers, big long vector of numbers, into a single number to give us an objective that we can optimize. Now, whether you call that an aggregation or whether you call it merging, it amounts to the same thing. In some literature, so this paper I allude to, they talk about merging functions. And so they asked this question. They said, suppose your measurements, suppose your raw numbers were measurements that were on an interval scale, as per the previous slide. And suppose you want to aggregate them together, merge them together to come up with a single number. What kind of function should you use in order to do that? In order to answer the question, they impose a few other kind of mild conditions. So one of them they call agreement, and that's simply, suppose I've got a stack of numbers, n numbers, they all take the value c, then what I would like is when I aggregate them together, I get the value c. Right? This makes sense, right? It's a mild condition, we can state it like that. So if we just define the standard deviation, this is a usual definition, so this paper proves this result, right? It's a bit of work to prove, and I know it looks a little daunting at first, but let's just unpack it. What it says is that any aggregating function that is invariant on an interval scale and satisfies agreement must take that form. So S is the standard deviation. It's measuring the overall variation. The E is the usual expectation. But look at the, and F is some arbitrary, is an arbitrary function on this set V, right? So why it ends up that way, don't worry too much. But the thing I want to draw your attention to is contrast that formula for A of X with this one that we met 2 weeks ago for these coherent risk measures. Remember, I said every regular measure of risk can always be written as a deviation measure plus an expectation. Look at what we've got over here. So that first term for the expression for A of X, it's a deviation measure. And indeed, you see S of X, that's the standard deviation, and then you've got some weird nonlinear scaling, an arbitrary nonlinear scaling. So this is a special case of that, but intriguingly, this is of the form that you get just from the starting point that I gave. Namely, we want to be invariant to the interval transformations. This is all that you can do. So in a sense, we've come to this proposal via a different route. This is much prettier than that. It's often the case that, when you've got multiple people coming from different starting points, one of them is going to be nice and slick and the other one's not. But having the multiple viewpoints, I think, is interesting, right? Especially for a topic like the one that we're interested in, where we don't really know what this fairness thing is, right? We're trying to invent something, and if we just pull it out of the air and say, well, I like the look of this, that's not going to go and convince very many other people. But if instead you say, look, I start from all of these different viewpoints, all of them are reasonable, you can pick whichever one that you want, I follow the logic, and look, I end up at the same point, that's more compelling, I think. So, let's join the dots of what we've seen. Since the different types of measurement scale demand different means of aggregation, and the different types of sociality are claimed to be the result of different primary motives. So that's the sociologist's theory. So, I didn't mention this already, but in his work, he claims that what underpins those 4 different types of sociality are these different motives, like the deep, what is it that the society is trying to achieve, right? For example, unity, the motive to care for and support the integrity of in-groups by avoiding or eliminating threats from the outside, right? That's a fine motive, right? You can think of a society motivated by that. Or hierarchy, right? The motive to respect rank in social groups. Like, you must know some people who think that this is very important. Some people think that's more important than the other one, and vice versa. Equality, the motive for balanced in-kind reciprocity. Also a reasonable motive. And the final one, proportionality. If you work harder, shouldn't you get more reward? Again, some people think this, others not, right? The point is, all of those motives are kind of reasonable, but they're different. And those 4 are the motives that Fiske argues underpins his 4 types of sociality. So now, those first 2 points and our third one, fundamentally different types of social relationships, entail fundamentally different moralities. So this is why this is interesting for us. As engineers, we're trying to build these machines that encode some kind of ethical principle. But now we find actually, we can't even agree on the underlying motives of what's going on. Can we turn that arm-wavy argument into something mathematical? Well, indeed we can, right? This was my point, that you now have a connection between these different motives, the moral choices, and the types of sociality, and different fair means of aggregation. Now, when I say there's a connection, I'm not saying I can derive this as a theorem. You can only derive a theorem when you're staying within the world of mathematics. So we're playing this slightly dodgy game here. We were looking at some analogies. We're looking for a theory of how societies think about things, and we've got our mathematics, and we're trying to match them up. That's what we're trying to do. Anyway, so we should not be surprised that this notions of fairness and ethics are essentially contested. So you can, build a table like this. I'll let you dig into this if it excites you. I'm not sure how significant all of those columns are. I've just taken them from the literature that I give here. But the thing I want to point out is on the left-hand column, that's the elementary form of sociality. And what Fiske says in his book, this is not my idea, I'm just copying what he's done, is he relates communal sharing to the categorical measurement scale, authority ranking to the ordinal scale, equality matching to the interval scale, and market pricing to the ratio scale. Depending on the choice of scale, you've got a different kind of form of sociality. So the one that we're playing with, the ratio scale, we're turning everything into money, which is good because that's what our society likes to do. So we can fit in with that. Right, so what? So I've already said that. This does not mean we can necessarily derive the right thing to do mathematically. Maybe it'll help us getting it badly wrong. The thing is, we're not measuring one thing, but an aggregate. And let me just reflect on that notion of the aggregate. And I found this quote quite intriguing. So this is a book, it's called Moral Aggregation. So as a mathematician, what I think of as aggregation is quite clear. I've got a stack of numbers, like the height of all of you in the room. And I can go and say the average height. It means something. I'm not sure what the value of that is, right? But we can go and do that sort of thing. Or I could take the maximum height, which would be useful if I'm designing a doorway, right? So we often have a need to reduce a stack of numbers to a single number on purely, engineering type grounds. This fellow says what I've written here. Some ethical theories tolerate or require a trade-off of different morally relevant factors. I call the trade-off of different morally relevant factors aggregation. So I found this intriguing. Remember in the first lecture, I introduced the particular notions of fairness, and then I introduced the notion of a fairness trade-off. Many moral philosophers will say, they've said to me, if you end up with a solution that has a trade-off, you haven't set the problem up correctly. You ask any engineer I know, they would say, of course, every problem in the world must have a trade-off. Right? It's called the engineer's tripod, better, cheaper, faster, pick any two. You think about it, you want to design a car, you've got to trade off the cost, the safety, ease of manufacture, how fast it can go, how many kids you can put in the back, right? So, how many of you think everything in the world is a trade-off? Who doesn't think that? Okay, good. We've got a couple of people to argue with. Yeah, so think about this, right? Because from the technologist's perspective, you have to grapple with trade-offs. And I think especially when you take into account that different people have different moral theories, right? You might think this is the right way to be fair. You might think this is the right way to be fair. We've got to balance these things out. What are you going to do other than trade them off, right? The only alternative is to basically say, you're completely wrong and you're completely right. That never seems to end well. So this motivates us to think a little harder about approaching this question of aggregation axiomatically. We already did that in the previous lecture. I gave you some axioms that gave you the coherent risk measure. So in a way, I'm just doing it again in a slightly more complicated fashion. Again, this is as a heuristic, this is a good approach. Just because you get to a result, right? You do all your work, you get a result. The usual, instinct is to say, great, I'm done, let's go and move on to the next result. Often a better plan is to say, that's good, now do it again, right? Do it again better, do it again differently. You've made a nice painting, good for you. Now make it better, right? So that's what we're going to do. So I'm going to show you a big stack of axioms on the next slide. It's something for you to go and look at afterwards. You won't be able to absorb it in the few seconds that I put up. But I want to just show you the richness of the choice, right? So far what I gave you, I chose a particular set of them, Or rather, I introduced these things, these coherent risk measures, and I said, oh, look, it satisfies these 7 axioms. And I could justify them. That looked nice, right? It looked like we're finished, right? We're ready to wrap it up and put a bow on it. Now, I want to point out, actually, we had quite a few other choices that we could have made, right? So it's important to think about that. So there's some technicalities some notational technicalities I have to introduce to state these explicitly. But as I said, this is something that you should just read. I'm not asking you to memorize it. Like one of the nice things about the course, I'm not asking you to memorize anything at all. All you have to memorize is when the lecture's on or when the tute's on or when your assignment's due. It's the only memory work. So they're all rather simple. We've met some of them before: positive homogeneity, translation equivariance and agreement, and monotonicity. And then there's a bunch of others, and there's all sorts of intricate interrelationships between these. And there's a lot that you can do with this, but we're not going to do it. The only reason for me to put up there is, what I'm saying here. There's several different ways in the literature where people describe the same thing, so I'm communicating that to you. What I had on the previous slide that I called rearrangement invariance is just a generalization of permutation invariance to a more general setting. Positive homogeneity, that's just unitary scaling. That's like a ratio scale, right? The Stevens ratio scale. I can either measure in meters or millimeters or kilometers. It doesn't matter as long as I'm consistent, right? It has certain other properties that are nice for machine learning optimization. If you have a loss function and you minimize the average loss, and you replace your loss function by 10 times that loss. It's a new loss function, you've just multiplied it by 10. The minimum value, of course, is going to be different. It's going to be 10 times higher, but the argmin doesn't change. And it's the argmin that your learning algorithm spits out. So positive homogeneity implies what I've called argmin invariance. And it turns out that there's, nice combinations. You combine this one with that one, right? But I don't want to get stuck on that. And using the terminology that I adopted here, the coherent measures of risk that we met in lecture 2 satisfy those axioms there, right? Positive homogeneity, translation equivariance, agreement, convexity, lower semi-continuity, rearrangement invariance, which is permutation invariance, and I can't even remember what NT stands for. Non-triviality. Oh, there we go. Yes, it's not identically zero. Right, big deal. Right, so you can approach this in various different ways. You can come up with all of these different aggregation functions. Your moral intuition about fairness can be captured in terms of how you aggregate. Do we take the average? Do we take the max? Do we take something in between? And different people do come up with different choices, and I'll cite some empirical literature on this in due course. Right, so it's not just me saying this anecdotally. People have gone and studied this in laboratory settings to see how people do these moral trade-offs in closed world scenarios. But now I want to point out, I think this is an intriguing result that grapples with the following question. So I've said that the choice matters, but many people will come up with different choices. So if we go back and grapple with that, you come up with a way of aggregating. You're very happy about it. You come up with a way of aggregating, and you're very happy with it. But they're different. What are we going to do?
Aggregate them?
Yes. Why not? Why not? It seems a natural thing to do. I mean, you could just say, well, go outside with edged weapons and whoever comes in alive would, right? There's that approach. Or you try and find some compromise, right? So that's what we're going to do. So this is the manager's approach. Okay, you guys can't agree. We'll find some compromise. Let's think about that, and let's think how much progress we can make on it. So the degrees of freedom might seem disturbing. There's a lot of them. So what we might do is as follows. Suppose we've actually got n people, and they all choose their own aggregation function AI, right? And to be able to give you a formal result, I have to make some choices. right? So in particular, I choose these. This corresponds to the coherent risk measures, but I'm ignoring continuity, right? Convexity, monotonicity, agreement, positive homogeneity, non-triviality, and rearrangement invariance. And now what we're going to do is we're going to construct a meta-aggregator, right? So that's a function that eats aggregation functions, right? We make this magic psi, it eats a bunch of these and spits out an A, right? That's not so hard to do, but we demand that if all of these satisfy those axioms, then this must also satisfy these. Otherwise, it's a big mess, right? That's a perfectly precisely defined mathematical problem. And the interesting conclusion is, so here I've written it in pure symbols, but what that says, let me just say it in words, the degrees of freedom that you have in choosing these measures is exactly the same as the degrees of freedom that you have in choosing the psi. Right? So just let that sink in. You've got all these choices, you end up choosing your A1. You have all of these choices, you choose A2. You choose A3. Now your job is to come along and find some kind of compromise, and the degrees of freedom that you've got in making the meta-aggregator are just as rich, right? So there's no simple way out, right? If you thought that you could avoid the necessity of choice just by clever management, you can't, because now all eyes are on here. You say this is the way to aggregate, but then she says, no, I'd aggregate it a different way. And then you could have a meta-aggregator, right? And so on, all the way up, right? It doesn't actually solve anything. I think that's kind of cool. I don't know. Computer scientists like recursion, don't they? I thought it was nice. Anyway, so in the slides, so as I said, I think walking through proofs presented on here doesn't work because you're not going to be able to keep up with what my argument shows. But the architecture of the proof is extremely straightforward. All you do is you take each of those properties and then you check whether it satisfies, right? And you check that you need to, that it ends up being necessary that psi satisfies the same properties as the original A1 and A2. Anyway, I'll let you look at that. So you can see it's all straightforward. I believe I've typed it out explicitly. So just in different words, what I've already said, the question of choosing a means of combining different aggregation functions in a manner which ensures the result satisfies the same properties has at least as large a choice set as the question of choosing A in the first place. So no escape by going meta. Would have been good if it did, but it doesn't. There's no easy problem to this question of choice. So we better understand our choices better. So that's a kind of a bummer. Here's another bummer. I know that's a lot of words. Let me explain what's going on. In most of the approaches to fairness, you have to choose some sensitive attribute. That effectively is partitioning the population. I could go and say, all the people with red shirts on, blue shirts or whatever, right? I've petitioned the class and then I want to be fair against that petition. Or maybe it's hair color or height or where you were born. There's lots of choices there. And these are actually a lot more palpable, right? This is not just some abstract mathematical function. I mean, let's make it real. Is it more important to be fair across race or sex? Many people would say, why don't we do both? But there's a problem here. You can't do it on everything. You start intersecting every requirement. That's also impossible. So we can ask this question. What we can do, so again, I've tried to make it formal so you can read it afterwards to check the argument. Finding subgroups, I can recast that as just making a petition, right? I got a set of n elements, I make a petition, So that's just putting them into disjoint sets such that the union of those subsets is the original set. So that's the notion of a partition. And what we're proposing to do is we then are going to aggregate like this. Within a group, we'll just average. So this was the proposal I put last week. I get all of the red people, I average their attributes. I get all of the people with blue shirts, I average them, right? All we're doing is we're just being fair relative to the subgroup averages, right? That's how the proposal I put to you 2 weeks ago works, right? So the question is, can you set things up in such a manner that you can be, consistently, can you be consistently fair across all possible subgroups, right? Now observe that if instead of using some fancy aggregation function, we just use the average, this all works, right? If I, remember, it's just the law of iterated expectations, right? The way I've set it up here. If I take, let's do it with height. If I take the average height of people with red shirts, the average height of people with blue shirts, with white shirts, I do that exhaustively. I weight things by the number of elements in each group. Then I take the average of the averages. I end up with the average height of everybody in the room. That works fine, right? And crucially, it doesn't matter if I decompose the class according to shirt color or hair color, right? I'll still get the right answer. Can you do the same trick using an aggregation function that actually penalizes inequity? Because the expectation doesn't, if you remember from lecture 2. That's the question. So anyway, you can follow the maths, I hope, offline, but this is the claim that I demonstrate, and the proof's only a page, I think. We pick a coherent risk measure that gives us the specific axioms, and we demand that it's inequity averse, which basically says it can't be expectation. Right? Every coherent risk measure except expectation is inequity averse. That means you pay a price for the deviation. Mathematically, it's just that its value is larger than the average value. So you can't choose one of these that's inequity averse and what I call subgroup invariant, which means that you get the same answer whether we partition on shirt color or hair color or any other grouping like that. And what's the point of a theoretical result like that? The point is, it looks like the choice of groups is a problem, right? I mean, people will disagree. Is race or sex the more important thing? It makes sense to go and ask the question, can we sidestep it? Could we come up with a scheme that somehow magically quotients that out? So it doesn't matter that you like to think about race, you like to think about sex. I don't know if you like to think about sex, but sex equity. So this is my point. If you want to penalise unfairness, then you will not be able to get the same answer regardless of the petition. The petition unavoidably will change your objective, and thus, likely but not guaranteed, your solution obtained by optimising the objective. So what I've been doing here is we've come up with a proposal, and now I'm trying to find holes in it, right? And this is always a good thing to do. Anyway, there's a proof which I'm not going to walk through live. You can see it's there, right? It's easy, right? It's 2 pages. Please study that. I can talk to you about it if you want. There's nothing deep, right? It's just bookkeeping. So what do? There is a way out of this dilemma. What that claim says is you can't deal with every subgroup. But what you could do is you can make every individual their own group. In other words, you could just dispense with the notion of groups. And then it all works, right? And I actually illustrated this in the lecture 2. So it's just in lecture 4, we'll talk about another approach to individual fairness. But I think this is worth thinking about. And there's another general lesson to learn there. We're grappling with how can we be fair to all of these different petitions. Oh my God, it's a big mess, right? And we then go and prove a theorem that says we can't possibly do it. Do we despair? No, we just backtrack further and say, why do we impose the groups in the first place? Do we need a notion of groups in order to talk about fairness? Now, a lot of people like the notion of groups, but it's not logically necessary. So that was the point, right? So these analytical exercises I'm showing you, the whole purpose is to, it's to test our thinking, like whether have we formulated the problem the best possible way? Given the difficulty of our task, your presumption should always be almost certainly not, right? So you come up with an answer, you should then immediately attack it and find the holes in it. All right, 3 o'clock, we take a 5-minute break.
Ja, wahrscheinlich nach diesem Semester die Masterarbeit. Aber genau, also hoffe ich, weil nächste Woche Mittwoch werden die Credits übertragen von Frankreich nachgegeben. Ich weiß natürlich nicht genau was die sich da vorstellen. Oder was es noch für Bedingungen gibt, von denen ich nicht gehört habe. Aber die Sachen, wo Machine Learning, also dass die Sachen als Machine Learning angerechnet worden sind, das war ein bisschen so. Aber bei General Computer sagen, müsste das alles sein.
Degree of freedom, which is presented in this slide. Are we assuming n is about the same magnitude of m, or it doesn't matter? So I just want to ask the intuition on this.
Oh, I
If
see.
n is way larger than m, how does this?
Yeah. Hang on.
Jetzt mit dem Media.
I assume m.
Yeah, no. I remember the question. No, it doesn't matter, right? So, yeah, this is a very compact way of writing it, right? So that whole thing there, right? The set. Let's think what the set says. This is the set of size such that if all of these A's are in AM, it implies that psi is in AM.
Yeah, this
right?
is
Yep.
essentially what
That's
we
right.
found,
Yes. And now psi is something that eats n arguments. And, and the claim is that that set is a superset of
choosing
A sub n. So
yes.
n and m are actually arbitrary for this to work. I mean, it's going to be trivial if n or m equals 1, but otherwise, I don't think it matters. I mean, if you look at the proof, I don't think it matters.
Right.
But you have to. I mean, what I said in words is, it's a slight fib in the sense that when you go and talk about the degrees of freedom that you've got, you've always got to index that by n, right? You know, if you go and say, I mean, you could probably sidestep this by talking about, a polymorphic function, right? Saying instead of so normally when we think of a function, it's got a fixed type. We say, here's a function that takes 4 arguments, right? Or it can take 5 arguments or 6 arguments. And I can give you a template of how to go and do that, all right? And what I was talking about was a function that takes some arbitrary number n of arguments. N is arbitrary, but you've got to pick it, right? And for any n, then the logic goes in work.
Yeah, since this curly A set
Yes.
is the definition that it satisfies these axioms instead of
Yeah,
it
yeah,
has
yeah.
a particular
That's-
form. Yeah,
That's
how
right.
defined. Yeah,
So
yeah, I
that
understand. Yeah.
m is linked to that m.
This red thing is basically kind of restating this demand.
Yeah.
This. Yeah, well, when I thought about degree of freedom, I naturally thought about do we need like n greater than n? So
No, I don't think that. Okay, we carry on. By the way, the pictures are in Tasmania, a place called Cradle Mountain National Park. Very beautiful and empty place to go hiking. So now something a bit less dry. I know axiomatic reasoning is not for everyone's taste, and we do that. I don't think I'm going to do any more of that in the whole course. But so let's step back a bit and away from the maths. So being fair and equitable is somehow related to not just looking after yourself, right? Avoiding self-interest. And self-interest is to do with whether or not you can put yourself in another's shoes. So this is Alexander Pope, one of the finest poets in the English language. He had this very lovely line here. By the way, pelf is an archaic word for money. Otherwise it doesn't rhyme. Whatever passion, knowledge, fame or pelf, not one will change his neighbour with himself. Okay, just setting the scene here. And he goes on, right? He wrote a lot. Let me read this, and I want you to think about it. God loves from whole to parts, but human soul must rise from individual to the whole. Self-love but serves the virtuous mind to wake, as the small pebble stirs the peaceful lake. The centre moved, a circle straight succeeds, another still, and still another spreads. Friend, parent, neighbour, first it will embrace, his country next, and next all human race. So he's a theorist of fairness, right? He's thinking about, the last line in particular is like you focus on yourself, your family, your neighbours, your country, right? So you've got this expanding circle, as Peter Singer calls it. So people have thought about this. How do you avoid self-interest? How do you design some fair, equitable scheme that's not just benefiting you? And we can turn that into an engineering problem, right? Design a mechanism that prevents self-interest. How might we go about doing that? So there's two approaches. Well, there's many approaches, but there's two that I want to draw your attention to. So one of them is only make judgments about others on matters that will not affect you. All right? We give that a name. That's called the impartial observer. It sounds simple. Have a look at the Stanford Encyclopedia of Philosophy entry on impartiality, which just goes forever, right? Like most things in philosophy, that single simple word is actually a big complicated mess. The other one is this is the information theorist's perspective, I think, remove knowledge of yourself so that whatever you do cannot be motivated by self-interest. This is a more subtle solution. Rather than saying, here I am as Bob, and I have to act not in self-interest, so I should only make judgments about matters that will not affect me. I have to keep myself in mind. What if I erased myself? If I didn't know that I was me? Maybe I was you. If I imagined myself thinking in that way. So this was actually done, and it's called
I need a veil, I need a veil, I need a veil of ignorance. Why are men okay with women not having the right to vote? Because they're not women. Why do some white people support apartheid? Because they're not black. And why do rich people oppose redistributing wealth? Because they're not poor themselves. Behind the veil, you could be anyone, you could be anyone at all. You might be rich, you might be poor, you might be white, you might be black, you might be straight, you might be gay, you might be anyone at all. Behind the veil, you'd have the power to decide how society should be. you'd have the power. You'd have the power to decide the rules that govern you and me. And that's it. Behind a veil of ignorance, you deliberate on what rules should govern society. But since you don't know who you'll be in that society, then whatever rules you come up with, that's justice. But what would we actually decide? I need to imagine what it would be like behind the veil in the original position.
There is a veil, there is a veil, there is a veil of ignorance.
But how can I conceptualize it?
It is behind you, it is behind you.
That's a lovely image, but how can I use my reason to look behind me?
No, you idiot, it's literally behind you. Just turn 180 degrees.
Fairness! You're behind a veil? It seems there's some kind of metaphor here, but I can't put my finger on it.
That was John Rawls. He actually a stand-in. We'll meet the stand-in again later. The picture is from the Wikipedia article on the veil of ignorance, which explains it very succinctly. It's a very simple idea. You are going to design a society. You want to avoid self-interest, so you do so in a manner where you don't know your role. So I don't know that I'm a professor, right? I don't know that I'm Australian. I don't know that I'm male. I don't know that I'm 61 years old. All of those things, you imagine, suppose I didn't know that, you put yourself into that so-called original position. That's how he ran his argument, right? He wrote this big fat book on it. And so the question is, to consider the question of fairness from that position. You would then naturally avoid self-interest. Now, this alone does not solve the problem, but often with complicated problems, you do it in multiple steps, right? You work out, rather than just solving it, you go and think, well, how are we going to solve it? We come up with a bit of a methodology. Well, we don't want to go and do this because we're clearly going to get a bad answer. So that was the logic behind his idea. So it turns out, and so this is the empirical work that I alluded to earlier. So empirical work suggests that the veil is not needed in some cases because people do sometimes bend over backwards to engineer decisions to help others more than themselves. So you can read this. So the paper title is Harm to Others Outweighs Harm to Self in Moral Decision Making. Very elegant set of experiments where this is Molly Crockett and others, including Peter Diane, who's here in Tübingen, looked at lab situations where, the subjects were given these moral decision-making tasks. And the critical thing, the difference, the two things that they considered was, are you making decisions that only affect other people? Or are you making decisions that affect other people and yourself, right? And they instrumented that. They looked at, how people behaved. So I think that's interesting to look at. The introduction of uncertainty makes things much trickier, right? So it's one thing if you know everything, like we've got the cake, right? And we're dividing it up. But once we start mucking around with probabilities of having a cake, it becomes a lot more complicated. So, again, more work by Molly Crockett on this. So, if you've got a kind of a scientific type background, she's I don't know what you would call her. We're going to meet her later in the course, but she studies moral decision making from a very scientific perspective. So this is all very nice, and this Rawls veil of ignorance is famous in philosophy. What are the implications for fair machine learning? So I claim that these two proposals, the impartial observer and the veil of ignorance, you can think of them as information throttling. So John Harsanyi, who we'll meet shortly, he credits his use of the device of the impartial observer to earlier work by William Vickery, an economist, on the prevention of gerrymandering, which I'm just going to mention as a digression because I think it's very easy for people with an ML background to understand. So gerrymandering does anyone know what that word means? Some of you do, right. So it's, you have electoral districts, and if you're in power, you might get to choose where the electoral districts are. And you have a lot of freedom there. You can just engineer it so that the right people are in and the wrong people are out. So you can engineer the outcome, right? So clearly you want to avoid that. Well, I guess it depends, right? I mean, if you're the kind of, venal politician who wants to stay in power, you don't want to avoid it. Everybody else wants to avoid it. This is an example of the thing that you might want to avoid. This is one of the electoral districts in the US, all right? Looks a little contrived. The interesting thing about Vickery's proposal, so there's a lot of work where people grapple with this. So I've given a paper here. I love the title. It's called A Measure of Bizarreness in the Quarterly Journal of Political Science. So their approach, which I think is doomed to fail, is they'd look at that and say, that's a very bizarre looking shape. And then if you had something which is just like a circle or a hexagon, you'd say that's not bizarre. And then they just cook up a mathematical definition of what looks contrived. I don't think that's really going to work. Intriguingly, there's something that we already do in machine learning that works very nicely. So if you've done statistical learning theory, you know that to prove any bounds on the performance of a learning algorithm, first you choose your hypothesis class. And you have to fix that. And it can't be too big. Then you can optimize over that hypothesis class and do empirical risk minimization on it. And you can prove theorems about how well you will do on finite data. And those theorems depend upon how big the hypothesis class was. The critical thing was how many choices did you have? You have to declare your choices in advance, lock them down, and how many choices you have matters. Anyway, that was Hassani's motivation, and I thought this was interesting, right? So Vickery's insight is to limit a priori the information one can use, right? So he suggested, for example, let's just all agree, right, before we look at any data about who lives where and how they vote, no peeking, let's just agree that the only allowable shapes are such and such, right? Maybe there can be polygons with at most 10 vertices, or maybe, whatever, right? But the thing is, you agree on that first, then you look at the data. And this idea of not peeking at the data before is legitimate is standard in machine learning. Anyway, we'll come back to that later on when we look at the distinction between ex ante and ex post. So, interestingly, this notion of information throttling, so I'm using it in a kind of a slightly metaphorical sense, but it turns out that there's a surprising amount of scientific evidence that this is the way we do it ourselves. So Donald Pfaff, who's a neuroscientist in New York, he wrote this paper, it's a book rather, The Neuroscience of Fair Play, Why We Usually Follow the Golden Rule. And look at what he says. What circuitry in the brain could possibly produce behavior as universal and as flexible and yet as reliable as fair play? I mean, the point is, most people are morally nice much of the time. Believe it or not, according to my theory, this circuitry does not require fancy tricks of learning and memory, but instead makes use of the easiest brain process of all, the blurring and the forgetting of information. The neuroscientist reckons the way we do manage to be fair is to forget information. And in particular, blurring the identity of the other with oneself, just like the veil of ignorance. It's all in our head. So these same brains, and you can manipulate this, right? I don't have the chemicals here with me, but if I had myself a oxytocin spray, people have done lovely experiments on this. You get a room full of people, oxytocin's a hormone, you spray it in the room, you can ingest it as a vapor or whatever, and it makes people love each other. It really does. So if you want to have a good party, get yourself some oxytocin, is what I'm saying. Anyway, so there's a paper here, Proceedings of the National Academy of Sciences, Oxytocin Promotes Group Serving Dishonesty. You look after your group, right? You bond with your group, and you'll do whatever it takes to look after the group, even lying to the outgroup. That was the point. It's how to make tribes stronger. So, recall the line from Pope, friend, parent, neighbour, first it will embrace. His country next to next, all human race, right? We look locally first. And so, when we think of, this seems relevant to us grappling with group fairness and how we choose the groups. Anyway. Now, to connect all of this to the mathematical stuff that I've talked about, I need to show you a way of representing these risk measures. Now, unfortunately, to derive this, I need to rely upon some convex analysis, and probably, has anyone here done a course on convex analysis? Very good. Well, you'll know exactly what I'm talking about, but I don't want to presume everybody does. So I'm trying to talk at two different levels here. So the axioms we choose for these coherent risk measures, they imply lots of things, but three key ones are that our functionals, these risk functionals, are closed, convex, and positively homogeneous, sometimes called one homogeneous. That means, so this is a standard result in convex analysis, that means that they are support functions of a convex set. This is a profoundly important result. If you have a functional that is closed, convex, and one homogeneous, then it is a support function of a convex set, and every support function of a convex set is one of these things. What is a support function of a convex set? So that's the thing I can't really elaborate in the time that I've got. To do justice to it would take a long time. But I can actually just give you the formula. You just won't have the intuition about it. And it's simply this up here. Essentially what you do is, in our particular case, I specialized it to our particular case, is so we have these quantities. I have a Q, so you can just think of that as a vector if you like, and think of Z as a vector. And the expectation of the product of Z and Q is just the inner product, right? So that's the normal way you think of it. The green curly Q is a set. So this is a support function. You take the set, curly Q, and then you can use it to define a function like this, right? What is it? You can see that it's the function of Z. Pick any Z, plug it into this, it's a support function. And these things are super powerful in convex analysis because it allows you to go from having a convex set to a function that represents the set, and vice versa. If I have the function, the support function of the set, that's the second line here. So if I have the R, I can recover the Q. So I suspect if you hadn't seen it before, that'll seem a little mysterious. Just take that on authority for now. You can look that up on Wikipedia if you want, or do the convex analysis course. But this is a standard bijection. It's called the Radstrom embedding theorem. Allows you to go from one to the other. And it allows you to think about questions of geometry, the shapes of convex sets in n-dimensional or infinite dimensional spaces, in terms of functionals. Why does that help us? Well, it means that our risk functionals that we want to use for this fairness game, instead of thinking of, I have to choose a functional, which is kind of, I don't know, that feels a difficult challenge. How do I even choose that? How do I even write down what I've got? What this says is that instead I can choose the envelope. I can choose this set curly Q. So this is what I'm relying upon. So normally in convex analysis you would write it like this bilinear form. But of course this is a particular instance of that. It's just the expected value. We just think of these are random variables, right? They're just functions, right? And we just take this integral. Let me give you an example, right? So that hopefully it doesn't look quite so mysterious. I did introduce 2 weeks ago this particular functional called the conditional value at risk, CVAR. And it has a knob, alpha, that you can dial between 0 and 1, right? For any fixed value of alpha between 0 and 1, it turns out that I can always write CVAR alpha of Z as the support function of a particular set. And what is the particular set? It's this one here, right? I'm going to show you a picture on the next slide. It'll maybe give you some intuition about that. The point is, I've just given you an explicit formula for some Q's, right? So basically a sandwich between 0 and this 1 over 1 minus alpha, and I demand that the Q has an expectation of 1. Think of the Q. Q can be a general function, but you can just think of it as a vector. It's just think of it as a 3 vector, right? So it's a positive vector. every element is non-negative. Every element is less than or equal to 1 over 1 minus alpha. Alpha is between 0 and 1. When alpha equals 0, this is equal to 1. As alpha approaches 1, this becomes unbounded, right? So this is a knob, right? As we adjust alpha, this term comes down, right? The smallest value this term in blue can take is when alpha equals 1. When alpha equals 0, in which case it's 1. And we have this constraint here. Look, fully understanding that, I know is not entirely easy, but I just need to show you how I can tune my choice of risk measure by mucking around with the choice of envelope. So what I'm going to show you here is this set Q for these different CVAR alphas. So when alpha equals 0, you see right up the top there, it's in very small type, I'm sorry, alpha equals 0. So that set that we take the support function of is this dot here, right? So here I've got the simplex, right? So it's just the 3 simplex, and I've just got the dot in the barycenter of the simplex. It's just the single element set. And if you've done convex analysis, you know that the support function of a singleton is a linear functional. Lo and behold, expectation is a linear functional. And now what we'll do is we'll vary alpha. And as we increase alpha, this set will grow, and you see it's that whole triangle is growing, and then it crashes into the walls. So we've got that set in 3 dimensions. When alpha equals 1, sorry, it's on a loop. I wasn't fast enough. When alpha equals 1, it ends up spanning the whole simplex, right? So you have to think of this. You're looking at the intersection of the red thing and the simplex, right? You're not looking at the box itself. It's doing it again, good. Right? So just that triangle on the simplex. So this gives us some insight into what this weird thing is doing. You have to just believe me on that. But I'll show you, I do have a good reason to show you why, to introduce this representation. So for now, all you need to take away is choosing one of these functionals is choosing one of these convex sets. And with that representation, we can actually already get some nice insight into the structure of these risk measures, right? We've got this, the whole lecture is about the problem of the choice of fairness measure. So we could choose expectation, we could choose CVAR 0.2, CVAR 0.4, we could choose some other sort of thing, like the average of CVAR 0.2 and CVAR 0.4. We can then go and ask, what's the mathematical structure of that set? And it turns out that it's a lattice induced by the partial order of the sets. So if I've got 2 sets, like imagine I've got a circle and I've got a bigger circle that contains it, then this induces a lattice order, right? Just the subset inclusion. And because of this one-to-one correspondence, that implies an ordering of the risk measures. If we have Q1 as an envelope, and Q2 that contains it, then R1 is pointwise less than or equal to R2. We can start to understand the structure of our choices here. The largest set that we can have is the entire simplex. That corresponds to the max. The smallest one we can have corresponds to the expectation. And indeed, the expectation is always less than the max. This just tells us what's going on in between, all right? So you can work out, you know, the meet and the join. If you've met lattices before, you've done databases, I guess who's met lattice theory before? Oh, well, this is all just gobbledygook. Okay. If you ever meet lattice theory by studying relational databases, maybe that'll make a little more sense. So you can just delete that slide if you want. So what can we do with this? Well, the second half of the lecture started with this nice poem by Alexander Pope written in iambic pentameters, and I thought that was pretty good, so I thought I'd try my hand at it as well. So, there once were 2 fellows, both known as John. Both wrote great books you could write swear upon. Both most profound, with great skill, style, and technique. One's work was so great it was set to music. Both were damn sure of the secret of fair, and although good friends, they agreed not there. Should impartial observers judge the case, or a veil of ignorance ourselves embrace? The problem is this: who should we put first to our caring thought, the average or worst? So this does immense violence to the subtlety of their positions. They've written 2 great big books on it, and I've reduced it to just 10 lines of doggerel. But it actually captures something about the choice that we're grappling with in this lecture. So in our terminology, their 2 proposals, so this is John Rawls, this is John Harsanyi, their proposal was choosing the particular R. And Rawls chose the max. I mean, more formally, I've written it as the essential supremum, to be precise, when you're working with an uncountable set of possibilities. And his argument to get to this is long and complicated, but you can distill it as follows. You have a bunch of people in a society, and what are you trying to do? You're trying to, they've all got different wealths, they've all got different well-beings. You're concerned, what should you focus upon? The welfare of the best off, the average, or the worst off person? And Rawls would argue that you should always pay attention to the worst off. Now, we work with loss functions, so we've always got a minus sign that we're carrying around. So for us, we're always considering the max, right? The maximum loss is the worst that you can do, right? So I would argue that choosing the max corresponds to Rawls's position. So
I like to think of justice basically as fairness.
let's listen to his argument.
Justice has fairness. There's fairness in justice. Justice is fairness. It's so simple, so brilliant. Now all I need to do is express that in 500 pages and people might finally take me seriously. You have inspired me. What's your name? I shall call you fairness, like your hair, yes, and your smile, inspiring me to write a book in analytic style. These foolish kids could care less. Your awareness is beguiling. Let's join up as a pair if we lose this moment.
I'll be right back, Professor.
Anyway, so I know when I talk to moral philosophers about this, they think that just reducing his 400-page argument to just that mathematical formulation is completely missing the point. But Rawls himself says, page 121, if you get that far into the book, we should strive for a kind of moral geometry with all the rigour which its name connotes. Unhappily, the reasoning I shall give will fall far short of this, since it is highly intuitive throughout. Yet it is essential to have in mind the ideal one would like to achieve. Anyway, I always keep this in my pocket if I ever get beaten up by people who don't like the maths. And I would just say, well, what Rawls wanted to do, right, is to put it into maths. And the lovely thing is that he says he wants a geometry. So it's not just a moral geometry, it's a moral convex geometry. That's what we've got. Anyway, so that's his argument. No one's made a musical on John Harsanyi's work. This, you can find the recording of the entire show. It's hilariously stupid. A Theory of Justice, the musical. But Harsanyi's argument, which is in this paper around the same time as Rawls. So Rawls' original argument was 1958, Harsanyi 1955. Again, a great long argument, appealing to all sorts of moral philosophical ideas, to Kant and God knows what. He concluded that what instead you should do is to just look after the average. Now, this choice of risk measures gives you everything in between. So, my point in the lecture was choosing in between. Let's look at interpolating in between them. Because just saying, well, you can take the average or the max is not terribly insightful. So what we're going to do is look at what lives in between. And one class of things that lives in between is this conditional value at risk. And the way you can think about that, as I said, is in terms of the envelope. Now, one thing just to keep in mind for the demonstration I'm going to give you, so if we've got a bunch of n numbers and we want to average them, it's clear what we mean, right? We just go and average them. I can rewrite, if instead I want to go and take the max, then I can do the following slightly perverse thing. First, I take all of my numbers. And what I'm going to do is I'm going to take a weighted average of the numbers, right? I put a bunch of weights on all of the numbers. The weights have to sum up to 1, say. And now I'm going to optimize to get the largest value possible. I'm still only going to take an average. I'm not going to take a max of my measurements. I'm going to take a maximum over all choices of weights, right? So the max over the weighted average of the numbers that I've been given. And it should be clear to you, if you think about this for a sec, that if I do that, that does give me the max of the numbers that I was given, right? Because all you end up doing is you end up putting all of the weight on the number that I was given that is the largest. That's the thing that gives you the max. So that's how you can express the max as a weighted average. And all of these things are weighted averages. And so what you would end up doing is, if you recall the cartoon picture from 2 weeks ago, each vertical coloured bar corresponds to a single data point. We have our machine learning model, right? We've got a fixed hypothesis here. And what we're doing is we're evaluating how good this is, right? So these are losses, remember? And so if we wanted to say, if we came up with a hypothesis that predicted like this, you look at it, 9 out of 10 people have got a very small loss. So on average, it's pretty good. But person number 2 has a very large loss. Now, if we took the average, we wouldn't pay any attention to that, would we, right? So in this particular case, if we allow the reweighting that I told you about, right, where you can put a different weight on each data point and maximize over that, we will put a lot of weight here, right? Actually, I need to correct myself. There's 2 things going on here. First thing I said was correct, but we're now thinking, how can I compute the max by reweighting the numbers that I've got? In order to be able to do that, I need to be able to put all of the weight on one of the particular numbers. That means that my upper limit has to be very high indeed. So this scenario will correspond to something close to the max. So here I've chosen alpha equals 0.8. So that makes this thing at height 5, right? Because it's 1 over 0.2. So this is close to the max. The max, this would be off the chart, and we would put all of our weight on here, right? So that's very close to the Rawlsian idea. We aggregate, when we aggregate, we pay all of our attention to the worst off. And then we can start going in between. So now I've chosen alpha is, where is it, 0.6, right? So this is halfway in between Rawls and Harsanyi. And you see I'm blurring Rawls and Harsanyi here, right? I'm interpolating the 2 Johns. And as this comes down, these numbers gradually, because we've got the requirement that they have to sum up to 1, right? I've got less wriggle room. And the further I push this down, eventually I get to the point that I've got no choice. And so I've just got the straight average, and that's the Harsanyi position. I don't know whether that helps you. You have to understand the this envelope representation. But if that didn't make sense to you, I have already suggested to you, you can just try mucking around in Python or something rather. I've given you the formula for this CVAR thing. Just get some intuition, right? All I'm after here is that you get some intuition that we've now got a knob, right, that can interpolate between these 2. So, you know, in the past, so I've said all of that. So if you look into the literature that's been spawned by Rawls and Hassani from 70 years ago, there's like so much, thousands of papers and books, people arguing, no, this is what you should do, no, this is what you should do. I've yet to see really anyone approach it in this fashion, where you say, rather than trying to answer the question, this is right or that is right, let's just look at everything in between and think about how we can interpolate. Because maybe we don't need to answer the question in that binary way. Maybe all we need to do is to give people a knob to adjust, and they'll choose something in between. So I've given you some pointers there that you can go and read. And I've given you some more, this slide's just got some more examples about that. You might have, if you've done any economics, you might have come across this thing called Knightian uncertainty. Has anyone ever heard of that? So Frank Knight, this is a long time ago, this is over 100 years ago, he made this distinction. So you're an investor, right? You're a businessman. And he drew a distinction between the two words of risk and uncertainty. So normally we kind of confound these together. You can do decision making under risk, and there's all sorts of books on that. Right? You'll say, well, there's a probability that there's going to be a drought of such and such, and probability that the supply chains will get disrupted of so and so. You go and do all of your calculation, you optimize your expected utility. That's decision making under risk. But Knight made the distinction to decision making under uncertainty, which is when you don't know the probabilities. Right? It's one thing to say, what are you going to do on the weekend if the probability of rain is 10%? It's another if I say, I can't tell you a probability, right? It's kind of cognitively worse, right? You've been told less information. So he made that distinction. Anyway, I simply observe that taking the Rawlsian position is like doing that. There's some other things you can look at if this excites you, but I will skip over that. Here's the intriguing thing. So this just could look like a mathematical exercise. Good for you, you can interpolate between these two things. But it turns out that when you go and look at empirical literature, I'm going to skip that, I'm conscious of the time. People have, like the experiments I alluded to earlier by Molly Crockett, they found ways of modeling what people did in real life situations. They gave them a whole bunch of moral choices to make, and they tried to put them essentially on this scale. Now, it's not quite on this scale. What they did was this here. So this is the min, right? So this is just a convex combination of the min and the sum. They were working with utilities instead of losses, so that's why it's the min instead of the max. It's kind of the same flavour as the CVAR, but it's not quite, which is a shame, because it would have been much nicer if they'd used CVAR. It's mathematically better, but the key point is that there's empirical tests where you find that depending upon the situation, people have different choices. In particular, when you are allocating to others, like when your choice affected what other people did, the average alpha was 0.22, and when you were just worrying about yourself, the average was 0.1. When you are worrying about others, people took more care about looking after the worst off. So this was interesting, right? Whereas if they're just looking after themselves, they're thinking, I'll be fine because it's just a game, right? They don't worry about it so much. So, if you're interested, you can read the paper. I've already said that. The key thing is that we've got a knob that we can adjust. And why am I so keen on knobs? Engineers love knobs, right? You think of any complicated machine you see in a movie, there's lots of knobs, right, to go and adjust. And why do you need them? Well, I think this is an interesting analog to reflect upon for our purposes. We're trying to design machine learning algorithms that can be used for people, all different sorts of people, different groups of people, different societies of people. The analogy is you're designing an aeroplane seat. So there's a nice story that I've linked to here where, the Air Force, US Air Force, whenever this was, 1950s, they're trying to train pilots to fly the aeroplanes, and they're having a lot of crashes. So, you know, they get some folks to investigate what's going on. Why do the pilots keep crashing? And it's like one of these stories you think, no, surely it can't be that. But it is. And the difficulty was that the seats were not the right size. Seats in the plane were not the right size because the folks who designed the plane, right, you're putting, you know, it's hard to design a plane. You've got to get the wings, the engine, all of this. Like, this is the serious engineering work. And yeah, sure, there's got to be a pilot. Fine, we give him a seat. And we'll just design the seat for the average size pilot, right? We can work out what the average size pilot is, fine. We put an average seat in, which is great for the average size pilot, but most pilots are not average. It turned out to really matter, right? So anyway, you can look this up, and I've found the original Air Force document, and it's in the reading, where they say, oh my gosh, you know, how stupid. Pilots come in all sorts of sizes, and we were just working with the average. Now, isn't that a good lesson for us machine learners to think about? So nowadays, you go into an airplane, there's lots of adjustments, right? So we've just kind of internalized that. And there's a interesting, deeper story about this. So this is just kind of verging on creepily bizarre, but the details are in the text over there. So this bunch of men, they were men, decided that they would find the ideal female form. And the way they did this was just to average. They got measurements on, I don't know, thousands of women, and they just had the hypothesis, which psychologically kind of works out well, that what people like, if you look at what is an attractive person, it's the average. So they worked this out, and they gave her a name. She's called Norma, and they even made a statue of her. It's just bizarre. You should read the story. It's kind of funny in a creepy way. But, you know, the people looked at this and said, well, yeah, but does Norma exist? They then went and went on a search across the US. They'd worked out the perfect shaped woman, so they went looking for her, right, to try and find her. Yeah, I'm not going to say any more. You can read that if you want. It's kind of cringy. But why is it cringy? It's because you're focusing upon the average. Now, what the lesson that many designers learned was that if you're designing a machine or anything like tables or a room or anything like that, people come in all sorts of different sizes. And so they started to document this really carefully, like systematically. So instead of talking about the average man, we've now got 1 percentile man, 50 percentile man, and 99 percentile man. So you can then tell, right? So if you're designing office furniture or whatever, you now know the range of variation that you have. And you could get one of these cool things. So I found this in a museum exhibit. And it's like a physical artifact that here we are, this is a person sitting down, and you can just dial it up, right? Here we've dialed it up to small woman. You want to design something for, I guess this is medium woman, you just turn the knob, and all of these numbers change, and then you'll know how high you should make the backrest and so on like that. So this, it looks funny, right? I see you're all smiling, but I think there's a nice, metaphor that I can draw there, which is, there's actually lots of them, right? So it's like, this is fascinating, right? So they're high resolution. You can zoom in on the slides and have a look at all of that. I'd love to have one of these things you could play with. But so people come in all sorts of different shapes and sizes. That's the point I'm belaboring to make. And so likewise, our moral intuitions. So this is work from Jonathan Haidt. We'll meet this again in lecture 6 when we talk about naturalizing ethics. So the paper is The New Synthesis in Moral Psychology. And he came up with this amazing insight. I'm almost finished, I know I'm slightly over time. He came up with this very intriguing insight, which is that you can segment the population of humanity into these various categories. He's got them here, very liberal, moderate, all the way to very conservative. You can think of that as, that's just political alignment. Some people have their politics on the left, some are on the right. It's just Who knows why? You know, if you're on the left, you think the people on the right are all idiots. If you're on the right, you think the people on the left are all idiots. What he found was that they made their moral judgments differently. This is the intriguing thing. And he broke it down into these 5 categories about the amount of attention that they pay when faced with various moral dilemmas. And the people over here, they pay a lot more attention to notions of fairness than the people on the right. The people on the right pay a lot more attention to notions of authority and purity. He spells out all of these things, right? So my point is not to go and analyze what all of these things mean. My point is simply, this is pretty interesting, that you can actually scientifically document the different approaches people have. These characteristics, they're stable through the lifetime. It's a personality attribute. It's like whether you're an introvert or an extrovert, it doesn't really change. I don't know if anyone knows why it is, but some people think that authority and purity are more important. Others think harm and fairness are more important. So the approach is, rather than saying, well, this is the true ethics and these people are mistaken, he's just saying, no, we study this as a natural phenomenon. I think this is relevant for people designing technological systems. You can't, even if you wanted to, like if you're over here, you're not going to be able to convince these people to change their mind, and vice versa. But maybe you can design a system that can be adapted to both of them. I think that's an intriguing idea. Anyway, so that's what we want. Similar design tools for these moral dimensions. So what have we covered today? It was all just one topic. This problem of choice of fairness measure, I couched it all in terms of these coherent risk measures because I could make a nice story there. We found all sorts of intriguing connections to measurement scales, the forms of sociality. We found that we can't solve the problem by going meta. We can't avoid the problem of choosing groups either. And this geometric representation, achieving what Rawls said that he wanted to do, actually gives us a nice handle on what's actually going on. And furthermore, it's got strong empirical support. It's not just a mathematical fantasy. And I concluded by arguing that the engineer's role is to provide good knobs. Thank you.